By now, you've likely heard of diffusion models, the powerhouse behind much of today's AI-generated content on the internet. But do you know that diffusion models are trained on a deceptively simple task? They take images, add noise to them, and then learn to remove that noise step by step. It might seem like a leap from cleaning up noisy pictures to generating stunning, high-definition images, right? Well, the secret lies in a remarkable yet obscure formula first introduced in a 1956 letter, never formally published, yet profoundly influential. So what's this formula? Let's dive in and find out. Noise in images refers to random variations in pixel values that corrupt the original signal, often manifesting as specks or graininess. This noise can arise from a variety of sources, including imperfections in the imaging device. For example, you may have noticed noise in your pictures when the lighting is low. In medical imaging, the type of noise often depends on the imaging modality. For instance, here on the left, you can see that ultrasound images are typically affected by speckle noise, while on the right, computed tomography scans commonly exhibit noise that can be modeled by a Poisson distribution. In fact, real-world noise is very often approximated using simplified mathematical models. Among the many ways to model noise, two of the most commonly used are Gaussian noise and Poisson noise. Gaussian noise, in particular, is widely studied both in traditional image processing but also in machine learning. In fact, Gaussian noise has some very nice properties, such as the fact that it is additive, meaning that we just add it to the pixel values. So no matter what the content of the image is, the noise will be kind of evenly distributed throughout the image. In Gaussian noise, random variations follow a normal distribution, with most values clustering around 0 and only a few extreme outliers. We can control the amount of noise using the standard deviation sigma of this Gaussian distribution. The bigger the standard deviation, the more noise will be present in the image. So now let's focus on how we can remove this specific type of noise using a deep autoencoder. Here is a typical autoencoder structure featuring an encoder, a low-dimensional latent space, and a decoder. In the case of a denoising autoencoder, the goal is to take noisy inputs and transform them into clean or at least less noisy outputs. But what kind of training loss do we use to achieve this? Well, I think you guessed it, it's the mean squared error loss, of course. However, note that we don't want the output to match the noisy input, otherwise we would just reconstruct a noisy image. Instead, we want it to match the original clean image. So, to train a denoising autoencoder, we typically need paired data, both the clean image and its corresponding corrupted version. The training objective is then simply to minimize the Euclidean distance between the output of the autoencoder and the clean image. And with the magic of optimization, this process results in an autoencoder that effectively removes noise, producing clean images from noisy ones. But here's the intriguing question. What exactly is the denoising operation F, mapping noisy images to clean ones, that the network tries to approximate? To understand what the denoising autoencoder is truly learning, we first need an intuitive representation of the process. Imagine that this 2D space represents the set of all possible 28 by 28 images. This space contains every conceivable arrangement of pixels to form an image, from completely random noise to semantically meaningful images like shapes, letters, or numbers. The key idea is that the set of meaningful images occupies only a tiny fraction of this vast space. This makes sense. Among all possible pixel arrangements, only a small subset can represent coherent and readable numbers, for example. In more precise terms, we can say that the set of images representing numbers lies on a lower dimensional manifold embedded within the much larger space of all possible pixel configurations. This idea is generally known as the Manifold Hypothesis. Now let's take these three images and imagine that they are part of our dataset. When we add noise to an image, we can think of it as slightly perturbing the data on the manifold, causing it to drift outside of this lower dimensional structure. These noisy images are not so far from the manifold, since they still contain most of the semantic information. The transformation learned by the denoising autoencoder is then essentially a mapping that projects noisy images back onto the manifold. In doing so, the model not only removes noise, but also learns the structure of the manifold itself. Another way of saying it is that it identifies patterns and features that define meaningful images, such as the shapes and structures of numbers. While this idea of projecting onto a manifold is compelling in theory, the question still remains, is this truly what's happening in practice? Now that we're talking about practice, do you know what's the best way to learn math? That's right, it's by practicing. And there's no better way to practice than with Brilliant. Brilliant is an amazing platform where you learn by doing, offering thousands of interactive lessons in math, data analysis, programming, and AI. If you enjoy my videos but sometimes struggle with the mathematics behind the concepts, Brilliant's math courses are a game changer. Their lessons focus on the fundamental tools and concepts that are essential across all fields of science. And if you're into machine learning, you know there's no getting around mastering algebra and calculus. So why not try Brilliant for free? Head over to brilliant.org/dpia, scan the QR code on screen, or click the link in the description to start your free 30-day trial. And you'll also get 20% off an annual premium subscription. And we're back to the topic. While the manifold hypothesis provides useful intuition, it is more of an approximate concept than a precise representation of what's happening here. To understand what our deep neural network is really doing, we need to dive into the details of the theory. Let's first introduce some notations. We work with clean data denoted as X and noisy data denoted as X tilde. This noisy data is obtained by adding noise sampled from a Gaussian distribution with a standard deviation of sigma. Our neural network is modeled by a function f with learnable parameters theta. When given a noisy input, this function outputs a denoised estimate x hat. As we mentioned before, our loss function is the mean squared error, so the squared difference between our clean data and our denoised estimate. We can actually rewrite the mean squared error as an expectation over our entire dataset and the distribution of noisy images. So when we train our network, what we are really doing is solving an optimization problem. This problem aims to find the set of parameters theta that minimizes this expectation. If we remove the mention to learnable parameters, this problem is about finding a function f that minimizes this quantity. This function is typically called the minimum mean squared error estimator. As the name suggests, it provides the best average reconstructions in terms of minimizing the squared error. Training our neural network with the MSE between clean and noisy data means we are approximating the MMSE denoiser. This is very good because the MMSE estimator has been studied in depth well before neural networks were a thing. A well-known result tells us that the MMSE estimator is the mean of the posterior distribution. If you need a refresher, the posterior distribution describes how likely a clean reconstruction x hat is, given the noisy measurement x tilde. This essentially means we are optimizing the model to provide the best average estimate of clean images, conditioned on noisy inputs. Now let's break this down with an example. Suppose we have a set of data points represented in blue here. There is an underlying unknown distribution governing this dataset, which we call the prior distribution, P of x. Now let's say we have a noisy observation, x tilde. The likelihood of x tilde given the true data x is Gaussian, because x tilde is corrupted by Gaussian noise. If we had access to the expression of the prior distribution governing our dataset, we could compute the exact posterior distribution, P of x given x tilde. From this posterior, we could, for instance, find the maximum a posteriori estimate, which corresponds to the most likely value of x given x tilde. This would give us the reconstruction that is the most likely given our noisy image. However, in practice, we don't know the prior distribution, so we don't know the posterior distribution either. But here's the cool part. Through its training objective, our neural network can return the mean of the posterior distribution. This tells us that the neural network implicitly learns some information about the prior distribution, even though it doesn't have direct access to it. Now we're starting to understand what the network is learning, but we can go even further. Now let's take a quick tangent to talk about scores. The score of a data distribution is the gradient of the log probability density function with respect to the data points. Most of the time, this quantity is easier to estimate than the actual probability density function. Indeed, probability density functions are often expressed as potentials, normalized by the integral of these potentials. You may recall that a probability density function must have an integral of 1, hence the need for this normalizing constant. But computing this integral is typically intractable, especially in high dimensions. However, when we take the logarithm and differentiate with respect to x, the normalizing constant vanishes. Despite this simplification, the score retains valuable information about the structure of the distribution. To make this more concrete, let's see a quick example. Let's take some points sampled from a 2D Gaussian, along with the level curves of the probability density function. The score function of this density forms a vector field, where larger arrows represent higher scores and smaller arrows represent lower scores. As you can see, the magnitude of the score is greater when we are far from high-density regions, so typically when we are far from the mean of this Gaussian. And you can also see that the score decreases as we approach the mean because it's the region of highest density. If we start at a random point and want to move toward regions of higher density, we can simply follow the score. Now here's an interesting connection. The minimum mean square error estimator is actually tied to the score of a probability distribution. However, it's not simply the score of the distribution that models our dataset of clean images. Before I can explicitly tell you the link between our neural network and the score, we need to take a second brief tangent. Let's first recall an interesting result from probability theory. If we take two independent random variables, x and y, and consider their sum z, we can explicitly compute the probability density function of z. The density function of z is equal to the convolution of the density functions of x and y. In our context, this means that adding Gaussian noise to a dataset of clean images is equivalent to convolving the density of the data distribution with a Gaussian filter. Put simply, adding noise to our images is like blurring the underlying data distribution. This result is quite intuitive, as you will see with this simple example. Imagine we have a few 2D data points and we sample new points by adding Gaussian noise to them. If the standard deviation of the noise is larger, the spread of these new points will also be larger. You see that we sort of blurred the distribution of our three initial points. Instead of distinct sharp data points, we now get clusters of red points around our initial blue dots. If we increase the amount of noise progressively, it becomes even more obvious that we are just applying an increasing amount of blur to the underlying data distribution. And with a lot of noise, you see that the distribution eventually becomes a large, indistinct cluster of points. Well, now we have all the ingredients for the big reveal. So here you can finally see the explicit formula that links our neural network to the score of the noisy data distribution. This formula is often called Tweedie's formula, and it was first introduced way back in 1956, long before neural networks or diffusion models were a thing. Interestingly, this formula wasn't originally part of a formal publication. Instead, it appeared in a letter from Maurice Tweedie, physicist and statistician, to Robbins Herbert, who later mentioned it in a conference paper. In my opinion, this small, unpublished piece of work has had a tremendous impact on machine learning, more than anyone could have anticipated. Originally, this formula ties the posterior mean to the score of the noisy data distribution. But as you probably remember, we know that our deep neural network approximates the posterior mean, so we have this equality with the neural network on the left side. So, what does this mean in practice? It means that our neural network is actually approximating the score of the noisy data distribution, which, as you may recall, is simply a smoothed version of the true data distribution. This also implies that applying the network is roughly equivalent to taking the input and adding a small gradient step in the direction of the score of the smoothed data distribution. In other words, the network moves its input closer to regions of the original data distribution which have higher density. Does it sound familiar? Well, yes, it's quite similar to the concept we discussed earlier about the Manifold Hypothesis, projecting the noisy data back onto the manifold of clean images. But this time we've derived everything rigorously from classic probability theory results. And now, we finally have a clear mathematical understanding of what our trained neural network is actually doing. Thank you so much for watching this video. Denoising autoencoders have lots of applications now.